Chapter 7 Chemical Reaction from the book Introductory Chemistry. By the end of this video, you will be able to identify a chemical reaction, to write balanced chemical equations. Also, you will be able to determine if a compound is soluble. You will predict and write equations for precipitation reactions. Also, you will be able to write molecular complete ionic and net ionic equation. You will understand and you will identify and write equation for acid-base reaction as well as for gas evolution reactions. You will be able to identify redox reactions, and also you will be able to identify and write equation for combustion reaction. Finally, you will be able to classify chemicals reactions. So, what are evidence for chemical reactions? In the classic grade school volcano, the baking soda, which is sodium bicarbonate, reacts with acetic acid and the vinegar to form carbon dioxide gas, water, and sodium acetate. The newly formed carbon dioxide bubbles out of the mixture, causing the eruption. Reactions that occur in liquids and form a gas are gas evolution reaction, as this one that we have here in this picture. That is the one that's baking soda, the reaction that is involved baking soda and vinegar to produce the carbon dioxide as a gas, and also water and sodium acetate. And the red food coloring help us to see those bubbles. What occurs inside the engines of the automobiles is another example of a chemical reaction. Gasoline is a composition of different kind of compounds. The most important one is the octane. Okay, so this one is the one that reacts with oxygen to produce carbon dioxide, water, and the energy that the engine needs to move the car. This type of reaction is known as the combustion. The combustion reaction in an automobile engine is when hydrocarbons such as octane from gasoline combine with oxygen from the air and react to form carbon dioxide and water. Combustion reactions are a subcategory of oxidation-reduction reaction in which electrons are transferred from one substance to another. And a little bit later, we're going to talk a little bit more, we're going to go more deep in this type of reaction of oxidation reaction. The laundry detergents are also another example of chemical reaction. Laundry detergents works better than soap because it contains substances that soften hard water. The hard water contains dissolved calcium and magnesium ions. These ions interfere with the action of soap by reacting with it to form a gray, slimy substance called curd or soap scum. If you have ever washed your clothes in ordinary soap, you may have noticed gray soap scum residues on your clothes. Here is an example of how can we identify hard water. The one in the left is soap with pure water, and the one in the right is soap with hard water. And as can you see, the formation of bubbles is more in the pure water because some of the soap in the hard water are reacting with those ions as calcium and magnesium. That is the definition of hard water, water that has dissolved ions of calcium and magnesium. And because of that, that soap are reacting with those ions, and they are not able to produce those bubbles as we can see here in the soap, in the pure water. Laundry detergents contain substances such as sodium carbonate that remove calcium and magnesium ions from water. The dissolved carbonate ions react with calcium and carbonate ions in the hard water to form solid calcium carbonate and solid magnesium carbonate. This solids settles to the bottom of the laundry mixture, resulting in the removal of the ions from water. And now the water will be more able to wash better the clothes with the detergents. Laundry detergents contain substances that react with the ions in hard water to immobilize them. Reactions such as these that form solid substances in water are precipitation reactions. So, we can have different evidence for a chemical reaction. If we could see the atoms and molecules that compose matter, we could easily identify a chemical reaction because atoms combine with other atoms to form compounds. That means that new molecules form, also that the original molecules decompose, and atoms in one molecule change place with atoms in another. So these are examples of how we can identify a chemical reaction, but it will be just if we can see at a molecular level. If we could see the atoms and molecules that compose matter, we could know a chemical reaction has occurred by observing these changes. Often, these molecular changes cause microscopic changes that we can directly experience. In summary, each of the following provides evidence of a chemical reaction. Number one, a color change. Before this beaker was with a clear solution, okay, and when we add something there, it turns to like purplish or fuchsia color. So that means that there is a chemical reaction occurs there. Also, the formation of a solid in a previously clear unclouded solution. So you can see that in the bottom part here, we can see something like a solid or sometimes like a foggy. So that means that you produce a solid, you precipitate something. Also, the formation of a gas. When you add a substance to a solution, that also will be an evidence of a chemical reaction. The emission of light is another example of an evidence for a chemical reaction. And the emission or absorption of heat. Okay, so the emission or or absorption of heat also is an evidence for a chemical reaction. A gas evolution reaction is the formation of a gas is evidence of a chemical reaction. Here we have this is Alka-Seltzer tablet in water and it's producing the gas. A precipitation reaction is the formation of a solid in a previously clear solution, and this is an evidence of a chemical reaction. So here we can see that previously was clear, as this we can see this part, but when we add some kind of reactant, it turns to reddish. And here we see that's this cloudy thing, so that means that there is a solid. You have done a precipitation reaction. Now, if I show you this is boiling water. This will represent a chemical reaction because we're producing here a gas. So that means that this is a chemical reaction. Well, we need to be careful because even though we are producing here a gas, that doesn't mean that it's because of chemical reaction. When when water boils, bubbles form and a gas is evolved, but not chemical reaction has occurred. So when we basically add heat to water, we are transforming the physical state of water from liquid to gas. There is no reaction involved in that process. So that's why this is not an example of a chemical reaction, even though we are producing a gas. Boiling water forms gaseous steam, but both water and steam are composed of water molecules. So we have water even though in a liquid or in a gas. So that's why this is not a good example or is not an example for a chemical reaction. Evidence of a chemical reaction. Change occurring at the atomic and molecular level determine whether a chemical reaction has occurred. Only chemical analysis that shows that the initial substances have changed into other substances conclusively proves that a chemical reaction has occurred. Chemical reactions may occur without any obvious signs, yet a chemical analysis may show that a reaction has indeed occurred. The changes occurring at the atomic and molecular level determine whether a chemical reaction has taken place. So let's talk a little bit about a chemical equation. We represent chemical reaction with chemical equations. The substances on the left side of the equations are the reactants, and the substances on the right side are the products. We often specify the state of each reactant or product in parentheses next to the formula. These are some abbreviations that we use when we talk that some of the compounds or molecules are in gas state. We use a G for liquid, L for solid, S for aqueous, AQ. Aqueous is when we are using water solutions. So for example, if you have a solution of sodium chloride, the sodium chloride that is a table salt, you know that you can dissolve that in water. So you have an aqueous solution of sodium chloride. When you use the liquid, it's when you have a pure substance. So for example, water, H2O, is a liquid. So let's see an example. The chemical equation for combustion of methane. The reaction occurring in natural gas flame is methane, that is CH4, reacting with oxygen, O2, to form carbon dioxide, CO2, and water. We represent this reaction with the following equation. This is the chemical equation. We have here at the left of the arrow, these are the reactants. At the right side, we have the products. And the left side of the reactants are the compounds that react to produce our products. So here, the reactants are methane and oxygen that produce carbon dioxide and water. Now, we also need to add the states of each of the compounds. So most of the time, the methane is a gas, so we use a G. Oxygen also is a gas. CO2 is a gas, and water also in this equation is going to be a gas. So we use our substrate of G as gas in parentheses. So, how many oxygen atoms are on each side of the equation? Here in the left side, remember that the oxygen is the red spheres, okay, here and here. So we have in the reactant 2 oxygens, and in the products we have 1, 2, 3 oxygens. So we have 2 atoms here of oxygen, 2 atoms here, and 1 atom here. So we have 3 atoms in the reactants, in the products, and 2 atoms of oxygen in the reactant. The left side of the equation has 2 oxygen atoms, and the right side of the equation has 3. Atoms cannot simply appear or disappear in chemical equation. We must account for the atoms on both sides as of the equation. So that means that we have an unbalanced chemical equation. We need to have a balanced chemical equation because we can create neither destroyed matter. So what happened with the hydrogens? If we look for the hydrogens, we have 4 hydrogens in the reactant. They are forming the molecule of methane. And we have 2 atoms of hydrogen in the molecule of water in the products. So also we have here a difference between atoms in each side of the equation. So to correct this problem, we must create a balanced equation. To balance an equation, we insert coefficients, not subscript, in front of the chemical formulas as needed to make the number of each type of atom in the reactants equal to the number of each type of atom in the products. So those coefficients, we can add it in front of any of the molecules of the equation. It could be the reactants or it could be also the products. Okay, so here we have an example of how can we balance this equation by adding a 2 in front of oxygen and a 2 in front of water. By doing this, now we have 1, 2, 3, 4 atoms of oxygen in the reactants, and we have 1, 2, 3, 4 atoms of oxygen in the product. When we count the hydrogens, We have one, two, three, four hydrogens in methane, and we have here one, two, three, four because we have two molecules of water. So that means that now we have four hydrogens and two oxygens by um, due to the presence of those molecules of water in the products. And also we have one carbon in methane and one carbon in carbon dioxide. So the equation is now balanced because the number or the numbers of each type of atom on both sides of the equations are equal. So we can check now the balance equation. The number of a particular type of atom within a chemical formula embedded in an equation is obtained by multiplying the subscript for the atom by the coefficient for the chemical formula. If there is no coefficient or subscript, a 1 is implied. The balance equation for the combustion of natural gas is as follows. CH4, methane, gas, plus 2 molecules of oxygen in form of gas would produce a molecule of carbon dioxide and plus 2 molecules of water, both of them in gas. So we have one atom of carbon here, 1 times CH4, because the only source of carbon that we have in the reactant is CH4. Okay, so that's why we multiply 1 times CH4. Also, for hydrogens, we have 4 atoms because we have one CH4, just one. We have 4 hydrogens here, and we have 4 atoms of oxygen because we have 2 molecules of O2. So that means that we have 4 oxygens. And doing the same thing with the products, we have 1 carbon from CO2. We have 4 hydrogens from water, okay, because we have 2 H2O. So that means that for each H2O we have 2 hydrogens. So we have 2 molecules of water. That means that we have 4 molecules of 4 atoms of hydrogens. And oxygens, we have 2 due to 1 molecule of CO2, and we have 2 because we have 2 molecules of water, and each molecule of water will provide 1 oxygen. So that means that we have 2 from water because we have 2 molecules of water, and 2 from O2. So that we have our 4 oxygen, and we have 4 oxygen in the reactants and 4 oxygens in the product. So that means that we have a balanced equation. So the number of each type of atom on both sides of the equation are equal. So the equation is balanced. A balanced chemicals equation represents a chemical reaction. In this image, methane molecules combine with oxygen to form carbon dioxide and water. So, how to write balanced chemicals equation? The first step is write a skeletal equation by writing correct chemical formulas for each of the reactants and products. We can review Chapter 5 for the nomenclature rules. If a skeletal equation is provided, skip this step and go to step 2. If an element occurs in only one compound on both sides of the equation, balance it first. If is more than one such element, balance metals before nonmetals. 3. If an element occurs as a free element on either side of the chemical equation, balance it last. Always balance free elements by adjusting the coefficient on the free element. Number 4, if balance equation contains coefficients fractions, change this into whole numbers by multiplying the entire equation by the appropriate factor. So if you have 1/2 of any of the molecule for any reason, you need to multiply all the equation by 2. So in that way, 1/2 times 2 is going to be equals to 1, and you can remove that fraction. So we're going to see an example in a few minutes. Number 5, check to make certain the equation is balanced by summing the total number of each type of atom on both sides of the equation. Remember, change only the coefficients to balance a chemical equation. Never change the subscript of any compound, because if you change the subscript, you have now a different molecule. Okay, so you never change the subscript of any compound to balance a chemical equation. You just add coefficients in front of any of the molecules of compound in the chemical equation. It could be in the reactants or it could be in the products. Let's see the following example. The reaction of solid aluminum with aqueous sulfuric acid to form aqueous aluminum sulfate and hydrogen gas. It's important to let you know that you may know how to um, draw the equation by just reading an example like this. So I suggest you to go to chapter 5 where we discuss the chemical nomenclature because sometimes you need to rewrite the equation right in the molecules itself because you're going to have just like a paragraph with the problem. So for this one, we have, for example, aluminum solid. So we can put aluminum and the S as subscript because this is the state and how you can find the aluminum. Sulfuric acid is an aqueous solution, so that's H2SO4 in aqueous solution. And then this will form the aluminum sulfate in aqueous solution also, and hydrogen gas, H2 gas. So this basically is that equation. So since both aluminum and hydrogen occurs as pure element, balance those last. Those are the last one that you're going to balance in this equation. Sulfur and oxygen occurs in only one compound and on each side of the equation, so we need to balance this first. But also, sulfur and oxygen are part of a polyatomic ion that stays intact on both sides of the equation. So you can see here that you have an SO4 and also you have an SO4 here. So that this is basically a polyatomic ion. So it must be treated as a unit. Okay, so balanced polyatomic ions such as these as a unit. So we have here 3 of this polyatomic um, ion, and we just have here 1. So that means that we need to add 3 of the sulfuric acid. So in that way, we can have 3 of the sulfate and also here 3 of the sulfate. Okay, so we have to add the coefficient. And remember that we just add coefficient numbers in front of any of the molecules or compounds in the chemical equation. We can change neither of the subscript. Okay, so we just add coefficients to the equation. So here we have been basically balanced the sulfurs and also the oxygen because we have 3 sulfurs and 4 oxygen, 4 times 3 and 1 times 3, and also the same thing here, 3 times 1, 3 times 4, 12. Okay, so we have 12 oxygens and 3 sulfur. Remember that this 3, okay, subscript outside the parenthesis will affect everything inside the parenthesis. So that means that if we have 3 of this, we have 3 of sulfur, 3 times 1, and we have 12 of oxygens, 3 times 4. So next we can balance the aluminum. We have 2 aluminums in the products right here. We just have 1 aluminum in the reactant. So we can add a coefficient in front of the aluminum that will be a 2. Okay, and that way we now have 2 aluminums and 2 aluminums. And now we can see that we have 6 hydrogen because when we add this 3 in front of the sulfuric acid, this 3 is not just going to affect the sulfate, also is going to affect the hydrogens, the amount of hydrogens. So now we have 6 hydrogens in the reactants because we have 3 times 2, 6 hydrogens, and we just have 2 hydrogens in the products. So if we need 6, we must multiply or use a coefficient of 3 in front of the hydrogen. So in that way, we can have 6 hydrogen in both sides. So the sum of the number of atoms on each side to make sure that the equation is balanced. We have 2 aluminums here. We have 2 aluminums from here. We have 6 hydrogens. 3 times 2 is 6 hydrogens. We have here 3 times 2 is 6 hydrogens. Also, we have 3 sulfurs. So we have 3 sulfur here, and because we have 3 of the polyatomic sulfate, we have 3 also sulfur here. And then we have the 12 atoms of oxygen in each side. So that's how we can balance a chemical equation. Okay, that's the way. Remember, in this case, the one of the trick is to use the SO4 as a unit because this one is a polyatomic ion. Now let's talk about aqueous solutions and solubility. These are terminology that is used for compounds that dissolve in water. A compound is soluble in a particular liquid if it dissolves in that liquid. So you can have some substances that can dissolve in water, okay, and also some substances that can be dissolved in other liquids that maybe they are not hydrophilic. They don't love like water. Maybe they can be dissolved in oil or can be dissolved in gasoline because both you can't mix gasoline and water, neither water to oil because of the properties of the intermolecular forces. They have different intermolecular forces. So maybe some compounds that are not solubles in water may be solubles in other liquids. Okay, so the thing is that you need to understand that solubility is going to depend also in the liquid that you're trying to dissolve the compound. Okay, so a compound is insoluble if it does not dissolve in the liquid. An aqueous solution is an homogeneous mixture of a substance with water. And when an ionic compound dissolves in water, they usually dissociate into their component ions. So when you have an ionic compound that dissolve in water, is not just dissolving the compound, also is separating those ions. Remember that an ionic compound is a compound that has a cation and an ion. So when it dissolves in water, if we have an aqueous solution dissolved in water, you are just not dissolving the compound, also separating those ions. And that process of separating the ion is called dissociation. So that's why we use here the word dissociated because we separate the ions. So one thing is dissolving, that when you are dissolving something, is just that compound be dissolved in a liquid, and dissociate is when you separate the ions in a specific liquid. So for example, we have a solution of sodium chloride, okay? And in a solution of sodium chloride, we don't have this NaCl units. We don't have the sodium chloride as a compound in water. They separate, they dissociate it, okay? So that's why we have ions in that solution. We have positive ions that are the sodium one, that are the purple spheres, and also the chlorine that are the green ones, the green spheres here. Okay, so when you separate those ions, you're doing a dissociation. Okay, and also they has been dissolved with water. That's why they are soluble in water. It's an aqueous solution. So only dissolved sodium ions and chlorine ions are present in this type of solution. Substances such as sodium chloride that completely dissociated into ions in solutions are called strong electrolytes. Okay, so this is an example of a strong electrolyte. Substances that dissolve completely and also dissociated completely in water. They are strong electrolytes. The ions can be good conductors. They can conduct electricity. Okay, so pure water, for example, does not conduct electricity because it doesn't have any type of ion. Now, if we add sodium chloride, then that solution can cause, a conductivity, and that will induce the bulb to light. Okay, so this is due to the presence of those ions. Solution as sodium chloride are called strong electrolyte solutions. So another characteristic of those strong electrolyte solutions is that they are really good conductors, okay, conductors of electricity. And it's important to you to understand that this is pure water. Sometimes if you have a sample of tap water, maybe you can see a little bit of light, but it's because you have ions in tap water. This one is just pure H2O. You don't have any kind of ions here, so that's why it can't conduct electricity. Now let's see another example of an ionic compound known as the silver nitrate, AgNO3. Silver nitrate solution does not contain any silver nitrate in it. Only dissolved silver ions and nitrate ions are present. Also, that means that the silver nitrate solution is a strong electrolyte solution. When compounds containing polyatomic ions such as nitrate dissolve, the polyatomic ion dissolve as intact units. So this is a polyatomic ion, this NO3. You don't separate nitrogen from oxygen. This is a whole unit, okay? That this polyatomic ion of nitrate. So that's why you keep that as NO3 minus, and the cation that will be in this case the silver. Now, let's see another example of an ionic compound. In this case, we're going to see silver chloride. Okay, silver chloride does not dissolve in water because not all the ionic compounds dissolve in water, and this is really important. It doesn't matter if you're an ionic compound, that doesn't mean necessarily that you could be dissolved in water. Some of them could be and some of them don't. Okay, so the silver chloride is an example that does not dissolve in water. Silver chloride remains as a solid within the liquid water. You can see here this solid, okay? You don't see here ions, separated ions in solution. You just see just a solid in the bottom of the liquid. It does not dissolve into independent ions, okay? The silver chloride, as well as other insoluble substances of ionic compound substances that don't dissolve in water, they basically are don't dissolve, neither dissociated. Okay, so we have some rules of this solubility. The first one is that a compound is soluble in a particular liquid if it dissolves in that liquid. A compound is insoluble if it does not dissolve in the liquid. For ionic compounds, empirical rules of solubility have been deduced from the observation of many compounds. And I would like to go back to this one because remember that it's going to depend on the liquid that you're trying to dissolve a compound. So most of the time we're going to look at solubility tables, and those solubility tables are usually using water as the medium to try to dissolve that compound. But sometimes a compound, as I mentioned before, could be insoluble in water but be soluble in other type of liquid. Okay, so let's see the following diagram. Compounds that are mostly soluble. Compounds that contains lithium, sodium, potassium, ammonium, NO3, and also oxalate, C2H3O2 minus. They will be soluble, okay, compounds that contains chlorine, bromine, and iodine. But if they contain silver, lead, and mercury, they will be no sol they won't be soluble. Okay, if they don't have those compounds, then will be basically insoluble. Okay, if they have this three ions, cations, they will be insoluble. If they are in combination with other cations, then they will be soluble. And compounds with sulfate, you need to check if they are doing a combination or a molecule with calcium or any of these cations. If no, they don't have that combination, they are soluble. But if they have any of those cations, that compound must be insoluble. So, for example, the solubility rules indicate that compounds containing the lithium ions are soluble. So compounds such as lithium bromide, lithium hydroxide, and lithium carbonate dissolve in water to form strong electrolyte solution. The solubility rules state that compounds containing the nitrate ions are soluble. Compounds such as silver nitrate, lead nitrate, and calcium nitrate dissolve in water to form strong electrolyte solution. So let's see another solubility rules. compounds that are mostly insoluble. Compounds containing hydroxide. OH, okay, this you're gonna see this a lot. Is a polyatomic ion. It's a combination of oxygen and hydrogen. It's called hydroxide ion. So, does this compound contains lithium, sodium, potassium, and ammonium? We mentioned before that any compound that has this cations, they will be soluble. So, if a hydroxide compound, okay, that contain this any of this, they are soluble. If not, if they contain, for example, calcium, strontium, and barium, they will be slightly soluble. If not, they will be insoluble. Okay, so these are basically some of the rules for the hydroxide compounds. Compounds that contain S minus 2 anions, the same thing here. If they contain any of this, as we saw before, the compound will be insoluble. Okay, if they contain this cation, they will be insoluble. If not, they will be insoluble. Okay, so with lithium, sodium, potassium, ammonium, any compound with those cations, they will be soluble. And compounds with carbonate and phosphate, the same rule, the first one that we saw before, without any of these cations. If they don't have any of these cations, they will be insoluble. If they have any of those cations, they will be soluble. So, mostly insoluble. Let's see some examples here. The solubility rules state that, with some exception, compounds containing carbonate ions are insoluble. So, for example, calcium carbonate, iron carbonate, strontium carbonate, and copper carbonate do not dissolve in water. Note that the solubility rules contain many exceptions. For example, even though they contain carbonate, but if they're paired with lithium, sodium, potassium, or ammonium, they will be soluble. Okay, so those compounds with any of those cations and carbonate will be soluble salts, soluble compounds. Here we have a table that you also have in your book, 7.2, table 7.2, that are also summary the rules that we saw in the previous slides, okay, about the different combination that could create a solid that could be soluble or insoluble. So now that we have been talking about the solubility rules, okay, now we can talk about precipitation reactions. Reactions in aqueous solution that forms a solid. Sometimes we can have two compounds, they are soluble in water, they can dissociate in water, and with the combination, we can combine the ions of one compound to the other one, then the new compound that you're producing, it could be insoluble in water. So you create a solid, and this is known as a precipitation. For example, sodium carbonate in laundry detergents reacts with dissolved magnesium and calcium ions to form solid that precipitate from the solution. These reactions are examples of precipitation reactions, reactions that form a solid called a precipitate upon mixing two aqueous solution. Let's see the following example. We have here the potassium iodide and silver nitrate, I mean lead nitrate. With a combination of these two, they are aqueous. You can see here that they are aqueous. So that means that they are dissolved, but also they are dissociated. Okay, if you have a solid here, that will be that even though they don't dissolve, so they can't be dissociated. But any ionic compound that you see that are aqueous, you can assume that also they are dissociated. So that means that you separate these ions, this cation of this anion and this cation of this polyatomic. There's another example of polyatomic, the nitrate anion. Okay, so now we can combine this anion with this cation and this anion with this cation. Okay, so lead will combine with iodine to produce lead iodine here, and the nitrate can combine with the potassium, the anion with the cation, one anion of this compound to the cation of the other one, to produce the potassium nitrate. Okay, and the lead iodine here is a solid. When, when a potassium iodide solution is mixed with lead nitrous solution, a brilliant yellow precipitate of PbI2 forms. Okay, so this is the solid. You can see that the solution turns a little bit foggy. Okay, and there's a solid there. So that solid is uh, PbI2. Okay, is insoluble. Okay, and as we mentioned before in the rules, okay, when you have iodine, they will be soluble with exception when they have, for example, silver, mercury, or lead. And this is one example of that lead of this of that exception. Okay, so even though you have iodine, that most of the time compound with iodine or fluorine or chlorine are soluble, with the exception when they are combined with silver, mercury, or lead. Now, when you mix a solution or two solution of, for example, potassium iodide with sodium chloride, there is no reaction, okay? Because the precipitation reaction did not occur always, okay, when mixing two aqueous solution. You need to see what are the possible products. So one of the product here will be potassium. This is the cation. So it will look for the anion of the other one that is chlorine. So it will be potassium chloride and sodium iodide. Okay, so in that case, both of them, sodium iodide, whenever you have a sodium ion, is going to be soluble. Whenever you have a product with chloride, okay, this will be soluble with the exception of silver and lead and also mercury, but you don't have that here. So that's why you don't have a precipitate. It's a no reaction because the possible products that you would produce by the combining the cation of this one with the anion of this one and the cation of this one with the anion of this one are also soluble in solution. So that's why you don't have any product with the combination of potassium iodide and sodium chloride. So predicting precipitation reactions. The key to predicting precipitation reaction is understanding that only insoluble compounds form precipitates, okay? Just the insoluble compounds are the ones that produce the precipitates. In a precipitation reaction, two solutions containing soluble compounds combine and an insoluble compound precipitate. So let's see another example here. Before mixing the potassium iodine with the lead nitrate, both basically are dissociated in the respective solutions. So we have here the potassium iodide and here the potassium nitrate. We can see when they has been added to the water, they dissolve and also they could be dissociated. Okay, so here we have the presence of the ions. In one beaker we have one of the solution and the other beaker we have the second solution. So the instant that the solutions are mixed, all four ions are present. When we mix together, they are present there, all the four ions. Okay, so now they have different options. For example, this cation could react with the iodine and produce the potassium iodide, but it will be dissolved also in water. And the other option is that this cation could interact with the nitrate as well. This cation of lead could interact with iodine or with the nitrate to produce a new compound. So that means that we have here, these are the original compounds, potassium iodide and lead nitrate. So we can combine this cation with this anion, okay, that will be this one, and also this cation with this anion, that could be the other possible product, okay. These are potentially insoluble products. So we need to look for the table and see which of them is, if they are both soluble or insoluble. So if the potential insoluble products are both soluble, then no reaction occurs. If one or both of the potentially insoluble products are insoluble, a precipitation reaction occurs. So, and the only way that we should know which one is which, if they are soluble or insoluble, is looking at the table, at the rules that we have saw before. In this case, so potassium nitrate is soluble, but lead iodide is insoluble. Okay, that's why eventually that will be the solid, and that's why here in the equation you must use the subscript of S because you're going to produce a solid. And this one will be aqueous because the potassium nitrate is a product that you will produce, but this one is soluble in water, so you're going to have the dissociation. They will be separated by ions, so that's why it's aqueous. It's not also solid. Okay, so that will be eventually the chemical equation for that reaction. So write an equation for precipitation reaction. Number one, you need to write an equation for the precipitation reaction that occurs, if any, when solutions of sodium carbonate and copper chloride are mixed. Okay, so we're gonna write first the reactants. We have here this sodium carbonate, okay, and here we have the copper chloride, and we need to combine the cation of this one with the anion of this one, and the cation of this one with the anion of the copper chloride. So we're going to produce NaCl and copper and carbonate. So make sure to write the correct formulas for the new ionic compound. That's also really, really important, okay? If you need two of the anion with one of the cation or vice versa, or you just need one and one, okay, it's very important to write the correct formula for the new ionic compound. Use the solubility rules to determine whether any of the potential new products are indeed soluble. So the two possible potential insoluble products are sodium chloride and copper carbonate. And remember that sodium has a charge of +1, okay, and chlorine, the charge is -1. So that's why you need just one and one because they will cancel between them. In the other side, we saw before that copper is copper 2, as it was in the name of that compound, copper 2. So that means that copper has a +2 charge, and carbonate is a -2 charge. So that's why you just need one and one. So this will be the correct formula for this ionic compound, and this one for the sodium chloride. So sodium chloride is soluble because compounds containing chlorine are usually soluble, and sodium is not an exception. And also the uh, and and the copper 2 carbonate isn't soluble, okay, because compounds containing carbonate are usually insoluble, with some exception as sodium and potassium, but copper is not one of those exceptions. Now, if all of the potentially insoluble products are soluble, there will be no precipitate. Write no reaction next to the arrow. But if one of the potentially insoluble products is insoluble, you need to write this formula as a product of the reaction using the S subscript, because this one indicates that this product is a solid, and write the soluble product with the aqueous subscript to indicate that that compound is aqueous. So here we have the two products of this reaction, and as we saw before, this one is a solid, it's a precipitate, okay? And sodium chloride is soluble in water, so that's why you use the aqueous solution. That means that you're going to have the presence of sodium ions and chlorine ions in that solution. And finally, you may balance the equation. Remember to adjust only the coefficients, not the subscript. Okay, so we just need to um, add any coefficients to balance this equation. In this case, we have two sodium here. We just have one, so that's why we add two sodium chloride. And that's the same way this is going to affect the chlorine. You have two chloride, but also in this compound you have the two chloride. So the only thing that you need to do to balance this equation was to add the coefficient 2 in front of the sodium chloride, and that way you have also one copper here, one polyatomic ion of carbonate, one polyatomic ion of carbonate, so you don't need to do anything else to balance this equation. Now there exist different type of chemical equations, okay? The first one is known as a molecular equation. It's an equation showing the complete neutral formulas for every compound in the reaction. So this is an example of a molecular equation. All the compounds are represented as molecules with also each subscript for each of them. Okay. The second chemical equation is known as the complete ionic equation. This shows aqueous ionic compound and normally dissociated in solution as they are actually present in solution. So for example, silver nitrate, as I mentioned before, this will give you a hint if that ionic compound is dissociated or not. When you have an aqueous solution, that means, oh sorry, that means um, that you're going to have this solid, okay, dissolved and dissociated in solution. So that means that you're going to have the ions separated in the solution. So that's why we write here the silver cation, +1 in aqueous solution, the nitrate also -1 in aqueous solution. Sodium chloride is also aqueous, so that means that it will be dissociated. So we can separate they by ions. So you have sodium positive and chlorine here, both of them aqueous. You write the arrow, and then you have the silver chloride. In this case, this is a solid, so that means that it's a product, is an ionic compound, but is not dissociated. So you need to put this as a whole complete compound because you don't have ions present of silver or chlorine because you're producing a solid that is not soluble in water. Okay, and sodium nitrate. This one is also soluble. You see here the aqueous solution. So that means you dissociate this one also, a sodium and nitrate. So here you have the complete ionic equations. Okay. When writing complete ionic equations, separate only aqueous ionic compounds into their constituent ions. Do not separate solid, liquid, or gaseous compounds. Okay, just separate those that are aqueous solution. Now, in the complete ionic equation, some of the ions in solutions appear unchanged on both sides of the equation. These ions are called spectator ions because they do not participate in the reaction. Okay, they are not part of the reaction that is taking place in this chemical reaction. Okay, these are, for example, nitrate. You have nitrate here and also nitrate here. You have sodium in the reactants and sodium in the products. So this type of ions, they are known as spectator ions, and they are all present in the complete ionic equation. They are present in the complete ionic equation. To simplify the equation and to more clearly show what is happening, spectator ions can be omitted. Equations such as this one, which shows only the species that actually participate in the reactions, are called the net ionic equation. So in the net ionic equation, you're going to show just the ions that are involved in the reaction. The spectator ions, you need to eliminate it, okay? In the complete ionic equation, you're going to have all the ions that are present in the reaction, okay? But here, you're going to show just the ones that are part of the real reaction, that is the production of silver chloride. This is the reaction that is occurring in this equation, okay, under this conditions. So we have the three type of equation. The first one is the molecular equation. It's a chemical equation showing the complete neutral formulas for every compound in a reaction. The second one is the complete ionic equation. Is a chemical equation showing all of the species as they are actually present in solution, including the spectator's ions. Okay, they are part of the complete ionic equation. And the last one is known as the net ionic equation. Is an equation showing only the species that actually participate in the reaction. So in the molecular equation, we're not going to have any kind of ion presence, okay? In the complete ionic equation, we're going to have all the ionic that could be present. Remember that you can't separate the solid, the liquid or you can separate the ions of solid, of liquids, or gas. You need to keep them as a whole compound because they are not soluble, they can be dissociated, okay? And in the ionic equation is basically the complete ionic equation without the spectator ions. So let's talk now about some types of chemical reaction. The first one is known as the acid-base reaction. The acid-base reactions are reactions that form water upon mixing upon mixing of an acid and a base. In this reaction, we have an acid. Most of the time, you're going to see the acid has a proton or an H in front. Start always with hydrogen, and the base usually use the hydroxide. Okay, the OH. So in an acid-base reaction, here is the cation. This one is the anion. So you combine H with OH to produce water, and sodium and chloride to produce sodium chloride, that is a salt. So in an acid-base reaction, you're going to produce always a water and a salt. Acid-base reactions are also called neutralization reaction. Generally forms water and ionic compound called a salt that usually remains dissolved, okay, in the solution. The net ionic equation for this reaction will be H positive plus the hydroxide ion to produce water. And that's why it is called also a reaction of neutralization, because the acid has a lower pH, a pH lower than 7, a base has a pH higher than 7, and a neutral solution will have a pH equals to 7. Water has a pH of 7. That's why it's called a neutralization, because you're producing water. You're producing a compound that has a neutral pH. Okay, so that's why the acid-base reaction also is known um, as a neutralization. So this is a table of the most common types of acid and base. As I mentioned before, you have here the H in front. So this it's behaving as a cation. The other things are behaving as the anion. And the bases, most of the time, you're going to see bases with the hydroxide ion here, OH, okay? And OH, remember that ion of hydroxide has a -1 charge, okay? It has a -1 charge. Another type of reactions is the gas evolution reaction. And as you expected, you need in this reaction to produce a gas. So this type of reaction, nitric acid with sodium carbonate, will produce H2CO3 plus NaNO3. As you can see here, these two products, they are aqueous. They are soluble in water. And they are not a gas, because if they were a gas, you would see here a G that represent that that compound is a gas. But the thing is that carbonic acid, that is this one, H2CO3, this is really, really unstable. And when it's produced, this will be decomposed and will produce water and CO2. And now you have here the gas. Okay, so because at the starting point, when you are establishing the possible products, you need to combine, remember, the cation with the anion. So it will be H and CO3. And because CO3 is -2, you need two hydrogens. So this will be H2CO3. And then sodium for the nitrate, cation with an ion. So you produce the sodium nitrate. So those are the two possible products, and they are okay. But the thing is that this one, that is the carbonic acid, this is really, really unstable. And once it's produced, it will decompose easily to produce water and CO2. And this is the gas that you watch when you're combining these two reactants. And finally, you need to balance the equation. So you have here, for example, 2 sodium. So you need 2 sodium from here. You add a coefficient of 2 in front of it. And because you have also the nitrate, and also you have just 2 hydrogens here, you have just 1 here, you need to add a coefficient of 2 in front of the nitric acid. So and that's where you have 2 hydrogens in this side, 2 hydrogens here, and also 2 nitrates. Remember that this is another example of a polyatomic ion. And you have here also 2 polyatomic ions of nitrate. Okay, so this is basically an example of a gas evolution reactions. And the following is a table that shows you those intermediate products, okay, that are produced that are unstable and eventually will be decomposed to produce this type of gas. Okay, so these are possible intermediate products that could be produced in some of the reactions that you're going to see, and they are also soluble in water, so they will be aqueous, these ones, but because they are unstable, then they will decompose and produce their respective gas. Here we have a table also of the different type of compounds that could induce this type of gas or produce this gas evolution reaction. So here we can see that the initial product will be basically, in this case, the carbonic acid, and then it produce H2CO2, H2O, and carbon dioxide. The same thing here, produce the SO2, the NH3. So these are examples of the gas evolution reaction. Now, this type of neutralizations are also sometimes part of a daily basis, specifically when we neutralize the excess of stomach acid. Your stomach normally contains acids, okay? It's a really, really strong acid that are involved in the food digestion. You need that acid to try to help in the digestion of the food. Antacids are over the counter medicines that work by reacting with a neutralization stomach acid. Antacid contains bases such as magnesium hydroxide, aluminum hydroxide, or sodium bicarbonate. Those are different type of antacids that will neutralize that acid in your stomach. The base in an antacid neutralize excess stomach acid, relieving heartburn and the acid stomach. Okay, so that's basically that neutralization type of reaction that is occurring even in our body. Okay, when we have that uh, heartburn, okay, due to those acids in the stomach, we drink any of this kind of antacid. Could be liquid, it could be tablets that we could chew them, and eventually those are basic compounds, antacid, that will neutralize that acid in our stomach, and we'll be feel better after that. Another type of reaction is the oxidation reduction reactions. Reactions involving the transfer of electrons are called oxidation reduction reactions or redox reaction. Redox reactions are responsible for the rusting of iron, the bleaching of hair, and the production of electricity in batteries. So that's why it's really, really important, sorry, to know a little bit of the oxidation reduction reaction. Many redox reactions involve the reaction of a substance with oxygen. Okay, many of those type of reaction will have oxygen involved as part of the reactants. A fundamental definition of oxidation is the loss of electrons. Okay, it could be oxidation is when you lost electrons, and if you lost electrons, you're going to be a more positive species because you lost electron. Okay, so your oxidation number is increasing. That charge of the ion is also known as the oxidation number. So if you're losing electrons, that charge must be more positive. Okay, so that increase in positive charge, that is an oxidation. The reduction, a fundamental definition, will be the gain of electrons. So if you gaining electrons, your charge is going to be now more negative. Okay, and that will be the reduction. Here we have a helpful mnemonics. Oil rig is the oxidation is loss and reduction is gain from a perspective of electron. Okay, in the oxidation you're losing electrons. In a reduction you're gaining electron. Also, you have here the Leo gear is lose electrons oxidation, gain electrons is reduction. So it's basically the same thing with another type of mnemonic. Notice that oxidation and reduction must occur together. Okay, so if one compound lose an electron, there must be another ion that needs to gain that electron. So the one that is losing the electron is experience a reduction, and the one that is gaining the electron is experience the reduction. Okay, so you have one oxidation
And as the same way you're having an oxidation, there must be another ion that will be experimenting the reduction. If one substance loses electron, that is oxidation, then another substance must gain electron, that is the reduction. For now, you simply need to be able to identify redox reaction. That's the only thing that you need to understand right now and to learn. A reaction can be classified as a redox reaction if it meets any one of these requirements. Redox reactions are those in which the following occur. Number one, a substance react with elemental oxygen. Okay, if a substance react with elemental oxygen, is an oxidation reduction reaction. Another one, number two, is a metal reacts with a nonmetal. That also will be an example of a redox reaction. And more generally, one substance transfer electrons to another substance. If you can identify that, that will be an example of a redox reaction. Combustion reactions are a type of redox reaction because in the combustion you need the presence of oxygen. Okay, combustion reactions are characterized by the reaction of a substance with oxygens to form one or more oxygen containing compounds, often including water. Combustion reactions are exothermic. That means that they emit heat. Compounds containing carbon and hydrogens are, or carbon, hydrogen, and oxygen, always form carbon dioxide and water upon combustion. Okay, always they will produce carbon dioxide and water upon combustion. And other combustion reactions include the reaction of carbon with oxygen to form carbon dioxide. So most of the time, the two possible products that you will have in a combustion reaction will be carbon dioxide and water. So this is basically a classification of a few samples of chemical reactions: precipitation reactions, acid-base reactions, gas evolution reactions, oxidation reduction reactions, and one example of this is the combustion. Now, reaction can be classified in four different ways. One of them could be synthesis of or combination. In a synthesis or combination, you are combining two compounds to just produce one. You will have two molecules and you produce one compound. In the composition, you will have one compound and then you will have two or more products. Okay, that will be the composition. You start with just one. The single displacement, here you can see that you have one element here. Okay, well, this could be a metal, and you have here a compound, and this one has a B and a C. This is a cation. This is an anion. So now with the A, you can displace the B and produce a cation from A, and then this cation will produce a neutral element. Okay, and this is a single displacement. The A displaced the B. Okay, to produce the AC plus the B that was displaced. And also could have a double displacement. You can see this one as the cation of this will interact with the anion of this, and the cation of molecule 1 will interact with the anion of molecule 2. That will be an example of double displacement. The synthesis reaction, two simpler substances combine to make a more complex substance. In this series of photographs, we see the sodium metal and gas chlorine. They are both here. Okay, when they combine, a chemical reactions occur that forms sodium chloride. The reaction is starting here, and eventually you will produce here the sodium chloride. So you start with sodium and chloride. Okay, here, and then you produce just sodium chloride. This will be an example of a synthesis, starting with thus two molecules and finishing with one. The decomposition reaction. In a decomposition reaction, a complex substances decomposes to form simpler substances. Okay, so from one, you're producing two or more. Okay, it could be two or more products or substances. When electrical current is passed through water, H2O, the water undergoes a decomposition reaction to form hydrogen gas and oxygen gas. Okay, so when you have here the water, okay, and you through the water, you basically pass an electrical current, then you can separate and you will have molecules of hydrogens and molecules of oxygen. Okay, so in that way, you started with one compound and you're producing two. So this is an example of a the composition reaction. The other one was the single displacement, and in this one, uh, in the displacement or single displacement reaction, one element displaces another to form a new compound. We can have, for example, this metal zinc when it's immersed in a solution of copper chloride. The zinc atoms displace the copper ions in solution. So here we have the zinc, okay, and the zinc will displace the copper. So you're going to produce a new compound of zinc chloride, and the copper in solution will start to deposit in this plate. Okay, so that's why you start to see the copper here as a solid. Okay, before was an ion, and now it's a solid, so it doesn't have any kind of charge. It's neutral. Okay, so the copper went from +2, okay, to 0. So that means that it went to a reduction. So that means that zinc experienced the oxidation and zinc went from 0 to +2. The last examples is double displacement reaction. And this one, two elements or groups of elements in two different compounds exchange places to form two new compounds. A double displacement basically has this general form, okay? AB plus CD producing AD, the cation of this one, with the anion of this one, plus BC. C is the cation of this one, and B is going to be the anion of this one. So this should be CB actually, because this the cation always needed it first. You needed to write it first. So the kinds of reactions that made B double displacement are precipitation reactions, acid base reaction, and also gas evolution reactions. So here we have a flow chart of the classification. Synthesis, okay, when you have two molecules and produce just one. Decomposition, when you from one you can produce two or more products. The single displacement, most of the time you're going to see like a metal, okay, displacing an a cation of another compound. And the double displacement, when you have both cations interact with the counter ion of the other compound, inducing this double displacement. So this will be all for chapter number 7, chemical reaction, from the book of introductory chemistry.